Hi everyone, I'm Chinmay. I'm a software engineer at ShareChat. Today, me and my colleague Anuraj will be going over ShareChat's journey in migrating 100 TB of data to ScyllaDB with no downtime. So, firstly, I wanted to start with why we chose ScyllaDB. So, we at ShareChat work at a pretty big scale. We have over 40 million monthly active users, and we wanted a database that is performant, cost effective, at the same time provides very good monitoring and resiliency. Moving on to the agenda now. So we'll firstly be going over the live migration framework overview. What is the problem that we are trying to solve? What is the overall architecture? Now, once we are thorough with it, we'll go over each of the components, like we'll deep dive into each of the components. We'll go over all the edge cases that we took care of. And at the end, we'll be sharing our learnings and results. Moving on to the live migration architecture. So firstly, our problem is twofold. When we talk about live migration, we need to make sure that the service that is serving the traffic is not disturbed. So we need to continue to serve our clients, which means that the primary DB cannot be turned off. At the same time, we also need to migrate all the data that is in primary DB to our new DB, which is ScyllaDB. So if you see from the diagram, we have a service. This service could be an application, a web server, or any other job. Within this service, we have something called a DB driver. I'll go into much deeper later on. Now, this service talks to the primary DB, which is its main database, which is responsible for reading and writing all the CRUD operations basically. Now, we also want to move to Scylla. So what we do as one of the phases is start doing dual writes. So we start writing both to primary DB as well as writing to ScyllaDB. Now, there could be multiple scenarios where this fails. Like, okay, our write to primary DB succeeds, but our write to secondary DB, which is ScyllaDB, fails. In that case, we have something called a failure recovery system, which is responsible for migrating those failed keys from primary DB to ScyllaDB. We also have an audit DB for auditing all our failures so that we can later on take a better look at why those fail. Another key component of this part is also config store, which basically helps DB driver access any of the tables in any of the databases that we use, be it ScyllaDB or otherwise. Another part which is important to is the exporting part, which is moving all the data from primary DB to ScyllaDB. So we have a job for this. I'll move on to deep dive into each of the components. So firstly, I'd like to start with DB driver. So DB driver is a key library that takes part in the live migration framework. So this is a one-stop shop for all the services to talk to any of the databases. This has wrappers to talk to all the databases that we generally use for NoSQL use cases. One of the important points of this is config store. Since DB driver is all about providing a uniform interface which is easy for services to access tables, we wanted to have all those configs stored in a store. And these configs actually contain information like the cluster information of the table that the table resides in, and so on. So config store becomes an important part of this. Now in ShareChat, we use multiple languages across all, and like the three primary of them are GoLang, Java, and NodeJS. Now we found that GoSQL and GoSQLX are pretty mature in terms of Scylla drivers. So we wanted to go with the Go route. So we have built our primary driver or library in GoLang. Now we also wanted to have support for NodeJS and Java drivers. There are other approaches. For example, we could have used a sidecar pattern, but we chose to go with the shared library approach. So we have a C++ wrapper on top of the Go driver. And then we have individual clients for NodeJS and Java, which basically uses the C++ wrapper to interact with the Go driver. This helps us because we do not duplicate the code. We just have to write a wrapper for each of the other languages. Also, if some other language comes along, they generally have a good interface with C++, and hence we do not have to replicate the logic for all the languages. Moving on, so how were we able to achieve the dual writes part? So I wanted to take a deeper look into DB driver. So if we look at DB driver, there are mainly three parts. One are the DB wrappers. Now these DB wrappers are basically responsible for doing CRUD operations in each of the individual databases. So we have a Scylla wrapper which does CRUD operation on Scylla. We have other wrappers which does CRUD operations on the other databases. Now, for migration purpose, we wrote another wrapper which uses all of these wrappers. So we have a migration wrapper. So this can use all the individual wrappers which can be used for doing CRUD operations in the individual databases. As I explained before, we definitely have a config store, which is also used now for having migration configs, which is basically, let's say, table A switches to table B, what does the field A maps to in table B, and so on. So all those migration configs are stored in config store. We also have API handler, which is basically the interface with which services and jobs use to interact with DB. Now, another essential part of this whole thing is also the failure recovery mechanism, because we have a possibility that the write to our primary DB succeeds, but the write to the secondary DB, which is ScyllaDB, fails. So in this case, we have a topic per table. And for each of these topics, we have two subscriptions. One is the migrator subscription, the other is audit subscription. Now, once, let's say, a key fails, so let's say I'm writing to row 1 and it fails, migration wrapper is responsible for pushing it to the public failure topic, and uh, and and we have a failure recovery system which has two jobs pertaining to each of the tables. One is the migrator, and another is the audit journal. The migrator is responsible for consuming from the migrator sub and reading that particular data from primary DB and writing it back to ScyllaDB. So we have consistency overall. Audit journal is basically to take whatever keys fail from the failure topic via the audit sub and pushing it to an audit DB. Moving on. So all seems good, but what about conflicts? Since we have two things going on parallel, one is dual writes, other is bulk import export. So in this case, there is a possibility that we are updating the same row key. So in this case, as you can see, we are updating the ID one. The service is doing a dual write on ID one, where it's changing the L name, last name to Kumar. At the same time, there is the bulk import export job happening, which is updating the F name and company. Now, what we used is Scylla's last write wins. For each of the cells that we have, which is for each of the columns, there is a time at which the data was written, and whatever was written later is finally stored. So in this case, since L name was updated later by this dual writes by the service, so that stays in the final data. The bulk import export job had L name and company written, so that stays in the final data. Now, what is important is we need to do the bulk import with a timestamp which is less than the timestamp that we start dual writes. And Raj will be taking a deeper look into this. Moving on. So now I'll go over the different migration stages that we have. So the first phase, which we start off, is dual writes enabled. So in this case, we are reading from source DB, but we are writing to both source DB and ScyllaDB. Remember, we haven't started the export job yet. Then we start off the export job. Still, we are writing to both the databases, but reading from the source database. Then we have an audit phase where during read phase, we read from source DB, but we also read from ScyllaDB and compare the data. And if there are any failures, we write to the failure topic, as mentioned before. But we keep on writing to both source DB and ScyllaDB. Then we also have a validation phase. So this happens for for mostly the live data. So people generally write a job which takes last 3 months or 6 months of data for all the rows, and they basically compare and say if there are any inconsistencies. And once all of this is done and we are happy with the consistency, we do a read switch. So we move the reads to Scylla, but still the writes happen to both SourceDB and ScyllaDB in case something bad happens and we want to switch over to SourceDB. Then finally the write switch, which is basically we have moved entirely to Scylla, and the reads and writes, everything is happening from ScyllaDB. So it seems like we are done with all the use cases, but what about counters? So let's take a simple scenario. Since atomic increments are non-idempotent calls, so we cannot use the same approach as before. Let's say we take a simple scenario. At time t1, we do a dual write into both the source DB and ScyllaDB. We increment the count to be count by 1 for ID1, So both in the source DB and ScyllaDB, the count becomes 1. Now let's say the export job picks up the same ID. It takes ID 1, it reads from source DB and tries to write to ScyllaDB. So the ScyllaDB count becomes 2, although in the source DB it remains as 1. So this is a problem. How do we go about solving it? So we basically split it into two phases. Initially, we do not start dual writes at the start. What we keep on doing is we start we start an initial phase which is write to key store. In this phase, what DB driver does is it writes to source DB, and instead of writing to ScyllaDB, it writes to a dirty key topic. Now this topic again has two subscriptions. One of that is a deduplication subscription, which is consumed by a collector job and which pushes all the keys to key store. The other subscription is not used in this phase. So this is the first phase. And in this phase, the export job has started. So the export is happening from source DB to ScyllaDB. No dual writes are happening. Write is happening to source DB and the dirty key, and all those keys are being moved to key store. In the second phase, once the export job is complete, what we do is we start with a partial dual write. So we do dual writes on source DB and ScyllaDB for keys which are not in key store. But migrator is responsible for migrating the keys that are in key store. So it uses the migrator subscription. It reads the data from source DB and moves to ScyllaDB. Now, once both of these phases are complete, if everything goes well, we have the data consistency because we did not do a double write on ScyllaDB for the keys that were used in the migration. Moving on. So the phases change a bit for the counters use case. So we have a writes to dirty key store phase where we are writing to source DB. We are not writing to ScyllaDB, but we are writing to a dirty key topic. This is important because we want to keep the ownership of those keys that happens during dual writes with the source DB for the time being. Once export job is complete, we start the dual writes, but this is again a partial dual writes phase, as we are as still the ownership of the non-migrated keys remain with the source DB. Now, once migrate dirty keys is over, then we have the complete dual writes on, and we can go on with the general phases of audit, validation, read, switch, and write. So now I'll be moving on to the details onto the export job.
Hey, hi everybody. This is Anuraj. I'm a software engineer at ShareChat. I'll be taking this presentation for explaining the export scenario. So in the previous part, Chinmoy explained how do we migrate the live data, the live traffic that is coming on the application to both the source and the ScyllaDB. And now I'll be taking you to explaining like how do we migrate the existing data which is there in the source DB already into the Scylla cluster, the ScyllaDB. So actually we had a lot of options of migrating the existing data to ScyllaDB. Either we would have written a custom GoLang or NodeJS based job which kind of reads the entire row set from the source DB and then keeps on writing those to ScyllaDB. However, there are three issues with this approach. First, the data set that we are talking about here is really large. So what happens is that once that particular, if there is a scenario that the source DB, I mean the jobs that we are writing, if any pods or any machine fails on that particular, it's hard to track like where we have read from the source DB until where we have returned to this ScyllaDB. Then there is already analytical jobs that are doing that particular purpose, right? So we should be going through the analytical job path. But then there is a scenario like how what approach we should take. Like either we should take a dump of that particular source DB into some distributed storage. Do we write a analytical job to do that purpose, and then from that particular storage we write another analytical job to read that particular data back into the ScyllaDB? Or either we directly connect both Scilla and the source DB with an analytical job, which would be kind of reading and then parsing that particular data, transforming into the data which Scilla understands, and then writing it again back to the ScyllaDB. So we chose a path where we will do this in a single job, so that it becomes more cost effective and more reliable towards our data transfer. So what happens now currently here, we actually chose to go with a Apache Beam programming model based analytical job, which can run on GCP data flow. We are using GCP ecosystem, so we used data flow to be our analytical job runtime. So here in this particular job, I'll explain like what is the structure of this particular job. So it basically contains three phases majorly. The first is a read part, so it kind of reads the entire row data, entire rows from the source DB in batched fashion, and then the second phase is the transforming those rows one by one into the row or the schema that our ScyllaDB have. So whatever table structure that we have in Scilla, we'll parse the source rows into that particular structure, and then in the third phase, we will kind of migrate all those data into ScyllaDB in a batched manner, so that it comes up with a lot more parallelism and a lot more speed that we can transfer our data. So because we are talking about here about a really huge data set. Okay, let's go to the next slide. So here, okay, so now let's since we spoke about three phases of our jobs, so let's see some code base, like how we actually what we actually do to read and transform and write that data, right? So these are the three phases. So since I spoke about in the previous slide that we are using Apache Beam based programming model here, so let me give some context about that. Like, so when we read a bulk data from Apache from any particular source connector here, we read it in the form of batch data. That group of data is actually called a P collection object in Apache Beam. That particular P collection contains a set of data that we want to apply some transforms or some functions on top of it. That function application of some operation on top of that data is called P transform, right? So here what we are doing is we are using a source database connector. So in Apache Beam programming model, we have connectors available to connect it with any source or thing. So here we are using some source DB connector to read data into a P collection is the first step of this particular job. That's a read part of the job. And then we are taking that particular source rows P collection, and we are applying a migrator function transform P transform on top of it to transform that particular read source rows into the destination rows. I mean the rows which are in structure or in schema of the ScyllaDB, right? And then we are taking that processed rows, and then we are finally applying a Cassandra IO. So the connector which is applicable here for sending the data back to Scilla is called a Cassandra IO connector. The good thing about Scilla is that it is blessed with the Cassandra ecosystem. So things which are applicable to a Cassandra database is also applicable to Scilla. So here we can use the Cassandra IO Apache Beam connector to write bulk data to ScyllaDB. Okay, let's see. There is one interesting problem in the next slide. Let's see that thing also. So now, till now, we in the last section on the live data, Cinema is, explained like the export jobs have to write data to ScyllaDB with a timestamp which is kind of lesser than the time lesser than the live traffic, right? So how do we make sure that whatever queries that are going through Cassandra IO, which are writing data to ScyllaDB from my export job, is always making sure a timestamp which is lesser than the timestamp which is coming up in the live traffic queries. So actually, we can provide this thing with a customization over the Cassandra IO. So Cassandra IO actually connector can accept a custom mapper factory, which can provide us a facility to provide a custom query, and then in a custom query we can provide actually a timestamp which we want to write the data with. So here we have actually provided a example of custom mapper factory, which kind of uses a custom object mapper. So in the next slide, let's see a custom object mapper, which essentially is so custom object mapper is essentially is a mapper implementation from the Cassandra driver actually, which kind of can provide us a save async method, which can use a table accessor from Cassandra driver, which can kind of use a custom query. We can provide a query which Cassandra IO should be writing to the ScyllaDB, right? So in this particular query, if you see here, we have provided an insert query, which is using a timestamp, which we can hard code here, whatever timestamp we want. So for example, the live traffic comes when we start the dual, right? That timestamp was T1, let's say. Then here in the using timestamp, we can provide a timestamp which is a bit lesser than the time T1, right? So this will make sure that whatever queries, whatever insert queries that we write into the ScyllaDB using Cassandra IO driver, that always goes through that particular hard-coded timestamp, which is always lesser than the when we start the dual, right? So that way we make sure that the conflict resolution is always handy. So okay, cool. Let's move on to the next slide. Cool. So let's discuss what are the challenges or the learnings through this particular entire live migration that journey that we had. So as the first challenge, we had we have the learning of write consistency. So whenever we are writing data to ScyllaDB through the export jobs, we know that we are writing very huge amount of data, maybe TBs of data, millions and billions of rows. So here the latency becomes really a important factor, so that our export jobs, our analytical jobs are very fast and writing data, reading and writing data. So here, if we have the write consistency level is 1, it is going to reply. The Scilla writes are going to be a little bit faster. They are going to reply faster, and in case of it's in comparison of quorum. However, the downside is that we might suffer a bit on the reliability of the data, right? In the second learning is and the partial data export. So we have some source DB connectors available in Apache Beam, which if the data size is really high, sometimes those connectors, in the Beam jobs, if the compute is not correct or the nodes are not scaling up properly, they might miss some data. They might, kind of lose some data, which is definitely not acceptable. So in those cases, we might need to export that data maybe to a intermediate storage step, and then maybe read it from that storage step to ScyllaDB to ensure that particular reliability and not lose any data. As the third step, we can say, as the third learning, we can say if the data is really huge, and if there are materialized views which also needs to be created on the Scilla table, it is better to create those materialized views after the export process has already happened, because export is going to increase the operations a lot more on the base table, and updating those materialized views in real time for those increased operations is not going to is always going to slow up the process. So it is better to create materialized views after the increased operations or the export job is finished. As a fourth learning, we can say it is important to use the right compaction strategy if we are exporting huge amount of data, and if we choose incremental compaction strategy, it is going to consume CPU and then do those compaction on a time to time basis, which is going to take up a lot of Scilla compute, and it's going to provide a lesser compute to the right operations that are happening. Sometimes it is better to use in null compaction strategy, let the data sink into the Scilla cluster, let the operations increase operations because of export jobs finished, and then we apply the right compaction strategy, whatever incremental, whatever we want for our database, right? And it's the fifth learning or the challenge. We can say that validations of that particular database, data which is there in the source database and the destination database after the migration, the export has finished, is also becomes a challenge, because here the analytical job that we will write has to read through each of the row key from the source, and then it has compared for the same thing in the destination ScyllaDB database. We have done a lot of kind of validations. For example, we might have taken 3 month data somewhere, keys of 3 month data in somewhere in some storage, and then compare those keys in source and destination database to make an understanding that we have the data completely synced in both source and destination database across the throughout the live migration process. The counters part is something I think Chinmay has already spoken about. So let's move on to the next slide. Cool. So now I want to discuss a bit on ShareChat's usage of ScyllaDB, how we are using ScyllaDB, at what scale we are using ScyllaDB. So till now we have already migrated 65 TB of data from our existing databases to ScyllaDB, and then we are in plan to onboard 50 more TBs of data to ScyllaDB, and around 35 to 40 services at scale are using ScyllaDB in ShareChat ecosystem. Currently, our biggest cluster size is around 28 TBs, and our max throughput for one of the cluster is around 1.5 million ops per second. So this is the scale that we are currently operating ScyllaDB at. Yeah. So with this, I think we are done with explaining how we have migrated this huge 100 TBs or more data to ScyllaDB. Right. Thank you so much for attending this talk. If you want to stay in touch, here are our contact details which you can